In this video, we'll keep talking about descriptive statistics, and we're going to explore more metrics to analyze data. So far, we have mentioned some centrality metrics, location metrics, and dispersion metrics. Now let's talk about shape metrics. So we will focus mainly in two shape metrics. Those are the skewness or asymmetry coefficient and the kurtosis. So let's get started with the skewness. What is the skewness? The skewness relates to the how symmetric or asymmetric it's our data. So pretty much we will look to the plot of the frequencies of the data that we have, and we will see whether the shape is symmetric or if it's skewed to the left or to the right. So let's see some of the possibilities here. So in the middle, here we don't have a skew. Please notice that this is a perfectly symmetric data. So in the y-axis the frequency, the x-axis refers to the values of the x variable. So please notice that the tails, the left and right tails in this case, both of them, they are pretty much the same thing, right? None of them it's longer than the other one. Therefore, we claim that that plot belongs to a symmetric data. Now, in some cases, it is possible that we have a longer tail that stands either to the left or to the right. So in this case here, when we talk about negatively skewed data, it's when the tail extends to the left. It goes to the left, we have a longer tail in that side. Therefore, we call it negatively skewed or skewed to the left. And the third case, it's a positively skewed. That's when the tail extends to the right. In that case, again, even though we have few observations here, there are some values with high magnitude. That's why we have a longer tail in that side. It's also important to mention what is the position of the mean, median, and mode. So we have perfect symmetry. The three of them are in the same place. The mean, median, and mode, they are the same if we have perfect symmetry. But when we have a distribution of data that is negatively skewed, please note that the mean is smaller than the median and the mode. Now, when we are dealing with a positively skewed distribution, then the mean is higher than the median and the mode. All right, so how can we measure if we have a symmetric or asymmetric data? So the way we do that is with this equation right here. So we require xi refers to the individual observations, x bar is the sample mean, s is the standard deviation, it's a dispersion matrix, and n refers to the number of observations. So it's just each individual observation minus the mean to the power of 3, the sum of all of those cubic differences, and then we divide the whole thing by n times standard deviation to the power of 3, and that's going to give us the skewness. So now, how can we interpret that number? So if the skewness is close to 0, if the metric is close to 0, that means that we have a symmetric data. We have symmetric data. It will be something like this plot in the middle. But if it's negative, like a negative number, then it will be more like negatively skewed. And if it's positive, it will tend more to be a positively skewed shape. So let's see these numbers that we have here. This is more like a guidelines to make the interpretation. So if the skewness is less than -1, that means minus 1.5, minus 2, or if it's greater than 1, then we will claim that it's highly skewed. If it's negative, then it will be highly skewed to the negative side. But if it's positive, then it will be highly skewed to the positive side or to the right side. Then, if the skewness is between -1 and -0.5, or if it's between positive 0.5 and positive 1, then it's moderately skewed. And finally, if it's between minus 0.5 and 0.5, that means like close to 0, then we will claim that it's approximately symmetric. You know that the 0, if it's equal to 0, it's perfectly symmetric, right? So if it's between minus 0.5 and 0.5, then it's approximately symmetric. So that's how we will interpret this skewness metric. Now, the second shape metric that we're going to discuss is the kurtosis. This metric, it's analyze, or it allow us to understand how's how tall or flat is our data. So this is like the reference. So when the kurtosis is equal to 3, this is the distribution that we have, like how tall it is. But if it's greater than 3, then it's going to be sharper, so we'll have a higher peak. But if the kurtosis is smaller than 3, then it's going to be like flat. It's going to tend to be flat. So please notice that the distance here between the maximum and the minimum is smaller compared to the other cases. So the skewness measures like if there is one tail that is longer than the other one, while the kurtosis measures how tall it's the frequency of some observation, like how big is the difference between the minimum frequency and the maximum frequency. That's like the idea that you get from the kurtosis, like if you have a sharp peak or a flat distribution in your data. So the equation looks similar, but the only difference is that instead of having to the power of 3 here, we have to the power of 4 in the numerator and denominator. So be careful. These metrics are, the equations are simple, but when you are doing manually, it will take a lot of time. This is how you can measure the skewness and kurtosis if you have an ungrouped frequency table. So remember that if you have the frequencies, it will save you some time. We did that when we were discussing the mean and this variance. Sometimes it's easier to introduce the frequency in the equations, because that will save you some time, or because otherwise you will need to find the difference for every single observation. But if you know the frequency, how many times each observation it's repeating in dataset, then it's faster, the calculation. So the equations are the same thing. The only change, if you notice, is that we're introducing here the frequency. So how many times we have a specific xi in our dataset. All right, so having said that, let's check this example. A company has developed three prototypes, set 1, set 2, and set 3. The company started to sell the products in the stores recently. The following table summarizes the sales of the products. So we have information about the 3 products, 1, 2, and 3. So we know which is this is the x value in the first column, x, that's x, and f refers to the frequency. That's the frequency, right? So how many times each value is repeated. So for example, this 5 means that the value 4, it's been repeated 5 times, right? That's the interpretation. So again, first column of each table is the variable, and f, it's the frequency. Okay, so the questions here, it's first, develop and analyze a histogram. So using the frequencies, let's plot that information. Then we're going to compute the mean, the median, and the mode. We will calculate skewness, and finally the kurtosis. So we begin with the histograms. So this is for set 1. So again, since we know the x values and we know the frequencies, so we can plot them easily. So we check the distribution, and if you notice, the tails, they look alike. There is no like a tail that is longer than the other one, right? So only by looking at this plot, we can claim that data looks symmetric, right? We need to confirm that later using the skewness metric, but at this point, using the plot, we can claim that most likely it is symmetric. So we expect that we're gonna get a metric close to 0 or even equal to 0. When we plot the second data set 2, the second product, please notice here that we have a left tail that is longer than the other one, right? So it's skewed to the left, negatively skewed. So we expect that the skewness in this case is negative. And in the third case, we have a tail longer that goes to the right. So this is skewed to the right or positively skewed. So now we can measure the mean, the mode, and find the median. So how can we get the mode? Is easy. The mode is just the value with the highest frequency. So we check here, this is the variable, the values of the variable. So now we check which value has the higher frequency. So the higher frequency is this one, 7, right? Therefore, when x is equal to 5, that's the mode. It's the value that gets repeated the most. That's for set 1. I'll do it for only for one set, and the other sets you use the same logic. All right, now if you want to find the average value, so the way it works, you have two options here. The long way will be, okay, we have only once, so it's 1. We have two 2's, right? 2, and the frequency is 2, so this is the 2 plus 2, and it continues. Then 3, we have 3 3's, so that's 3 plus 3 plus 3. Then there are 5 4's, so that's 4, 4, 5 times, right? So we keep going to the last one. So we know that 9's, there is only 1, right? The frequency is 1. And then we divide the whole thing by the number of observations, right? 29. So this is one way, right? This is the original equation that we cover for the sample mean. However, since we know the frequencies, it will be way faster to just multiply each x value times the frequency. So an alternative way, and you should get the same answer, will be 1 times 1, that's 1 of course, plus 2 times 2, plus 2 times 2, plus 3 times 3, right? I'm just multiplying x times the frequency, plus 4 times 5. And we keep going up to the last one, plus 9 times 1, divided by the number of observations, that's 29. So if you do that, you will get the mean value, which in this case is equal to 5. To find the median, let me erase here a little bit to make it a little bit more clear. Okay, so the way the median works, you have two options here. You can remember, use the if it's odd or even, or you can find Q2. So either way, that will be the median. So how many observations we have in this example? There are 29 observations, right? 29 observations. That's an odd number of observations. Then to get the median, we know that when we have an odd number, the median is going to be equal to the value of x that is located in the position n plus 1 divided by 2. That's when the number of observation is odd. So n plus 1 is 30, right? 29 plus 1 divided by 2, that's 15. So we know that the median in this data set is located in position 15. So how do we know where to get that position? That's when the cumulative frequency comes handy. If we compute the cumulative frequency, so we know the positions. For example, remember that this data is a range, right? From the lowest value to the largest value. So we know that here in the first class, there is only one value, so that's the first position. Then in the second class, there are 2, right? So up to here, we have the third position. So here we have position 2 and 3. Then in class 3, we know that we have from position 4 to position 6. Position 4, 5, 6, there are 3 observations. So we can keep going. So the cumulative frequency gives you an idea of like what is the position, or what are the positions that are located in that class. Then we need to find where the 15 is included. So we know that in this class, in the fourth class, we have up to position 11, right? But we're looking for position 15. Position 15 because here the median is located in position 15. That position, guys, is included in this class here, right? Because in this class, we know that the cumulative frequency is 18, right? Since the previous cumulative is 11, that means that the position 12, 13, 14, 15, 16, and 17, and 18, of course, are included in this class, right? So the 15, it's here. Therefore, what are the values that are located here? It's the same, right? Because there are 7 5s. So we have a 5 in position 12 up to position 18. That means that the position 15, it's a 5. The value that we have in that position, it's an x equal to 5. Therefore, the median here, it's equal to 5. So it's not a coincidence that the mean, the median, and the mode are equal to 5. That's because we have a symmetric distribution of the data. So once we have computed this information, we can get easily to the standard deviation. You find the variance first, and then the square root of the variance will give you the standard deviation. So you will use that column for that purpose. So remember that for the variance, we compute the difference between each observation minus the mean value, which we already know is 5, squared times the frequency. We add them up, right? And then we divide it over n minus 1. And that's going to give us the standard deviation. And remember that we require the standard deviation to compute skewness and kurtosis. So we can do the same thing for set 2. Same idea for set 3, to get the mean, median, and mode. I highly encourage you to practice, do it on your own by hand to get a better understanding. So with all the information complete, then you can find the skewness for the 3 sets. So the first one is 0. It is symmetric, right? And remember the plot of set 1. It is symmetric, so yes, it matches our expectation. Set 2, for set 2, it's minus 0.9. That's moderately skewed and skewed to the left. So the minus 0.9, yes, it makes sense, right? Because we have a longer tail going to the left. And the last one, we have 0.9 for set 3. It means that it's skewed to the right. And that's true because we have a longer tail that goes to the right. So finally, let's measure now the kurtosis. This one is not that simple to analyze because some plots are tricky. I will show you why. So remember that in the kurtosis, 3 is the reference. So if it's equal to 3, it's like a normal distribution. If it's greater than 3, it means that you have a sharp peak. But if it's less than 3, that means that you have a flat peak, right? Okay, so let's try to compare these 3. So we according to the numbers, in set 1 it's less than 3, so it's flat, it's flatter, right? Compared to the others. In set 2, it's 3.27, so the peak is gonna be sharp. And set 3, it's more like the normal height. So it's like not that big, it's not that sharp, not too much flat. All right, so let's compare them. So if we go to the first one, if you start looking at that plot, you don't see, you don't get why it's like less than 3. It doesn't make sense, right? Because it looks sharp. It looks sharp to me. Now, if I compare it with the next one, actually you will see, you might claim that in the first plot looks sharper than the second one, right? But that's because the frequency. So you gotta be careful because the scale is not the same. Here is 1 by 1, but if we check this one, it has increments of 5. So it's not the same, so you gotta be careful, right? Then a tip or a little advice that I may give you is that what you can do is compare the frequency of the highest value of the peak with the frequency with the lowest frequency. So this is 7, the highest, and this one is 1. So the distance between the lowest and the highest frequency is 6, right? 7 minus 1. But now, if we go to the second plot, please notice that the highest value of the frequency is 25, and the lowest it's 2. So that distance, it's way higher. It's bigger, right? 23. So you have a higher distance here between the minimum frequency and the maximum frequency. So that's suggesting that you have a sharper peak in the second set compared to the first one. And of course, we will experience a more moderate difference when we measure the kurtosis in the third one, because the distance here is between 1, that's the minimum frequency, and the maximum is 12, right? So the distance is 11, which is like kind of like in the middle of these two distances, right? So it is consistent with the numbers that we're getting here. It is consistent. So the first set has the lowest value of kurtosis, set 2 the highest value, and set 3 is the more moderate value of kurtosis. So just to summarize, we have two shape metrics, skewness and kurtosis. Skewness measures if your data is symmetric or not, and the kurtosis measures how sharp or flat is your peak. Okay guys, I'll see you in the next